Ever wonder how a massive video game keeps track of thousands of different characters, all doing their own thing at once? Or how a website like Amazon can juggle millions of products? Well, the secret sauce behind all of it is a really cool concept called object-oriented programming, or OOP for short. And at its heart, it's all about one simple idea, modeling the real world right there in the code. Okay, let's dive in and see how it all works. So here's the game plan. We're going to start with the big idea, this world of objects. Then we'll get into the nitty-gritty of classes, which are basically the master blueprints. After that, we'll see how you go from a blueprint to a real object, figure out where the computer keeps them, and then the fun part, making those objects actually do stuff. And we'll wrap up by looking at why this whole approach makes for way better code. Sound good? Let's get started. All right, first step, the world of objects. This is really the core strategy that programmers use to tackle huge, complex software without losing their minds. I mean, really, just think about that for a second. How on earth does a complex game handle every single car, person, and building all at the same time? Or how does a shopping site keep track of every single product, its price, how many are in stock, and all the customer reviews? It seems impossible, right? Well, the answer is actually pretty elegant. The software models all those real-life things as objects inside the code. To really wrap our heads around this, let's use an analogy for this whole explainer. Imagine we're running a high-tech car factory. You don't just start welding pieces of metal together randomly, do you? No way. You've got a plan, a process, a blueprint for everything. And that's exactly what object-oriented programming gives us. And that brings us to the most important part of our whole factory operation, the master blueprint. In the world of programming, we call this a class. You can think of a class kind of like a recipe for a cake. It's not the cake itself, right? It's just the instructions. It lists all the ingredients you need. We call those attributes, things like flour and sugar. And it gives you all the steps. We call those methods, like mix the batter and bake at 350 degrees. It's the plan, not the final product. So if our goal is to build this awesome car you see here, we can't just start building. First, we need to design the blueprint, the car class. This blueprint is going to define everything about what a car is and what a car can do, long before a single tire ever hits the assembly line. And this is where it gets really powerful. The blueprint has two main parts. On one side, you have the attributes. These are the things the car has. Its color, its current speed, the number of doors. On the other side, you have the methods. These are the things the car can do. It can accelerate, it can brake, it can turn on the radio. So this one blueprint defines all the possibilities. Okay, so our design team has perfected the blueprint. Now what? Well, it's time to send those plans down to the factory floor and build an actual physical car. And that is what an object is. It's the real deal, an actual instance that we create from our class blueprint. So while the blueprint just describes a car in general, an object is a specific car. It's the red Ferrari, and it's currently going 120 miles per hour. See the difference? It has a specific state, and it can do all the things we defined back in the blueprint. So how do we actually tell our code factory to build one? It's a cool three-step process. First up, declaration. We write car1. This is basically like calling ahead to the parking garage and saying, hey, I'm going to need a spot for a car soon. Save one for me. Next, instantiation. That's the new car part. This is the official order to the factory. Okay, build me a brand new car using the blueprint. And finally, initialization. We put it all together. Car1 equals new car. This is us grabbing the keys to that new car and parking it in the spot we reserved. And just like that, we have a real car object ready to drive.
This brings up a pretty interesting question, though. Once we build our car object, where does it, go? Well, inside a computer, this all happens in its memory.
And the memory is split into two important areas. Think of it like a huge parking garage. The heap is the main garage area, where all the actual physical cars, our objects, are parked. The stack is different. The stack is like the little ticket you get at the entrance. It doesn't hold the car. It just holds the parking spot number, a tiny, super fast reference that tells you exactly where to find your car in the giant garage. And this visual shows that perfectly. You see that reference on the stack? It's just a little pointer, like an address. It doesn't hold the big, complex car object. It just points you to where the actual object is living over there in the heap. It's a super efficient way for the computer to keep track of everything without getting bogged down. Okay, So we've designed our blueprint, we've built a car from it, and we know exactly where it's parked in memory. So what's next? Well, the whole point of having a car is to drive it, right? To get our object to do something, we use its methods. Remember those actions from our blueprint, like accelerate and brake? Well, a method is the block of code that has all the instructions for that action. But here's the key. It just sits there, waiting until we specifically tell it to run. We have to call it into action. And how do we do that? It's actually super simple. We use something called dot notation. You just name the object you want to talk to, in our case, car1, then you put a dot, and then you name the method you want it to perform, like accelerate. It's like pointing at your car and shouting, "Hey, car number 1, accelerate." That little dot is the magic that connects our object to all of its amazing abilities. Now, here's a great little pro tip for when you start writing your own methods. A lot of the time, a method's job is to figure something out and give you back an answer. It does that using the return keyword. But here's the catch, and you can see it right here. As soon as the computer hits that return line, the method is done. It's like a mic drop. Any code you write after the return statement is completely invisible. It will never, ever run. So, rule of thumb, return is always the very last thing you want your method to do. All right, for our last section, let's zoom all the way out. We've gone from a simple idea to a blueprint to a working car object. But why? Why go through all this trouble? Why is this object-oriented way of thinking the foundation for almost all modern software? Well, the benefits are huge. First, reusability. You write that car blueprint just once, and you can stamp out a million different, unique cars. Then there's hiding details. You don't need to be a mechanic to drive a car, you just press the gas. Same idea here. You can call the accelerate method without knowing how the code makes it happen. It also just makes your programs way easier to read. And maybe best of all, it makes changes a breeze. Want to add a turbo boost feature? You just update the master blueprint, and every single car you build from now on automatically gets it. It's brilliant. So that's really the big idea behind object-oriented programming. It's a powerful way of thinking that lets us build these incredibly complex systems in a way that's still organized and manageable. Now that you've seen how to build a blueprint for a car, what would you build next? A blueprint for a person, a building, a spaceship? The possibilities are literally endless.